We shall now discuss switched mode DC-DC converters. I mentioned earlier that DC-DC converters can be executed either using the linear circuits called the linear regulator circuits, which we discussed in the last week, or using a switched method by switching the semiconductor switches. In the case of the switched mode DC-DC converters, all the semiconductor switches, that is the diodes, the BJTs and the MOSFETs, they are all switched and they are either in the cutoff region or in the fully saturated region, which means all these switches are either fully off or fully on. The advantage in such mode of operation is that the switches which are coming in series will either be on or off, and when they are on, the current through them will be flowing through the on switch. However, the voltage across the switch is zero. When they are off, the voltage across the switch will be finite and the current through them will be zero. In both the cases, the power dissipated across the switches will be zero. Therefore, the efficiency will be very high. In an ideal case, the efficiency will go towards 100%. However, in a practical case, there will be switching transitions while going from on to off or off to on. The switch has to transit through the linear region, and therefore there will be some dissipation due to switching losses. And therefore the efficiency will not 100%, will not be 100%, but will be slightly lower than that. So we will take up now DC-DC converters using the switched mode technique, wherein the semiconductor switches will be switched. We will take simple converters and then gradually go to isolated converters and more realistic power supply cases. Let us now consider an unregulated DC voltage, and this DC voltage is supposed to supply power to a load or not. So let's say this input unregulated DC voltage is Vi, the output load is R0, load resistance is R0, and output voltage V0 is demanded, is required. Vi and V0 are different values, and therefore they cannot be just connected directly with the conductor. So they need to have some series element. In the linear regulator case, what did we do? We put a variable resistance component, which could be a resistance or it could be a semiconductor switch operated in the linear region. So basically this RS resistance was varied. So when this RS is varied accordingly, the drop across that varies, and therefore we could regulate V0. But unfortunately, there is a voltage drop across this RS, there is a current through RS, and therefore there is a power dissipation VRS into I0 happening in this resistor RS, and it is not available as useful load. Therefore the efficiency is very low. Now if we modify the constraint that RS can take only two values, it can either take 0 or RS can be infinite, that is open circuit. So let us put the constraint that RS is either 0 or infinity. In such a case, now let us plot V0 with respect to time. What happens? Let me make time divisions like this. Let me divide the time in this fashion. Now let us say first in this time, let us make RS is equal to 0. So this is 0. Vi comes completely directly to the output, and we will see an output like this with Vi. Now in this time region, let us make RS infinity, means open this. So when you open this, the entire Vi drops across this, and there is no load current, and therefore the voltage V0 across the load is 0. So this is what we have drawn there. Now let us make again RS is equal to 0. So this is shorted. Again Vi comes across V0, and therefore V0 is Vi. And RS infinity again, it repeats in this fashion if we take just only these two possible values of RS. Now if you see here Vi 0, Vi 0, these are the possible output voltage states. One thing that you observe from here, the output voltage is pulsating, not constant fixed DC. Another thing is we have restricted RS to only these two possible values, and when RS is 0, the voltage drop across RS is 0, and therefore there is no dissipation across RS. When RS is infinite, the current through RS is 0, and therefore there is no dissipation across RS. In both these conditions, the power dissipation across RS is 0. There is no power dissipation. So the entire power goes only to the load. The only drawback is that the output voltage is pulsating and not regulated DC. So one thing that we have achieved by doing this is to remove the power dissipation and improve the efficiency. Now to take care of this pulsating or chopped DC that is coming across the output, we need to put a filter. So we will put a filter which is non-dissipative. So we have to put a LC filter. So that is what we will do to obtain a DC again at the output. Let us now introduce a block there which is supposed to do filtering. So let us say that there are these components. The filter consists of three important components. One is the L or the inductor, which is the kinetic storage, C or the potential storage, capacitance, and there can be switch elements like diodes and other semiconductor switches. Now the filter comprises of these components. Now if I take before the filter VA, consider it as VA, now that will be chopped like that. And after the filter, the chopped waveform will be smoothened out, and that will be the smooth DC which will be applied to the load R0. So therefore, in a DC-DC converter, switched mode DC-DC converter, you have an input Vi unregulated, an output V0 regulated, different value. Now in between, there is a switch which chops the waveform. There are filters which will do the job of smoothing the chopped waveform to obtain a filtered DC. So these are the main components of a DC-DC converter. Now let us take the simplest DC-DC converter with one switch, one inductor and one capacitance. Let us now draw the circuit of a DC-DC converter with one switch, one L inductor and one capacitance. This is the load, and this is the input, unregulated input, L, C, R0. We have Vi unregulated, and this is V0. Okay. Now this is a single pole double throw switch. We call this as a pole P. This is throw 1. This is throw 2, double throw. So the most fundamental switch would be having a single pole and two throws. If one throw is not connected, then we call it as a single pole, single throw. But more fundamental is a double throw switch. So let us also make the connection for this throw T2, and let me connect this to ground. So which means throw T1 is connected to Vi, throw T2 is connected to ground, and the pole P will alternately connect to T1 and T2. So this is a full-fledged DC-DC converter. It has a single pole double throw switch, an inductor L, capacitor C. So this portion will be a switched mode power converter. Let us now have some clarity on when the pole will be connected to T1 and at what times the pole will be connected to T2. So let us make some definitions and clarifications on that. So for that, let us make some space, and I am going to have a graph of time versus amplitude here. But I am not going to use the y-axis. The time axis alone, I want to split it up into different periods of time. So let me make these kind of divisions in time, and let us see how these time divisions are defined, split and defined. So let us say this period, this is called TS switching period, and this is called again the next switching period TS. So this width period, time period is switching period. Now time period and switching period is divided into two parts. Okay, this switching period is also divided into two parts. So in part 1, let us say pole is connected to T1, and in part 2 here pole is connected to T2. Likewise, the next switching cycle, pole is connected to T1 during this period, and during this period pole is connected to T2. So let us say when pole is connected to T1, we will call that one as the on time. So I will say on. When pole is connected to T2, T1 is off. So I will call that one as off time. Pole is connected to T1, we will call that one as the on time. When pole is connected to T2, T1 is off, therefore we say that is the off time for T1. So with reference to T1, I am saying this is the on time, off time, on time, off time. Or symbolically we can say this is T on period, this is T off period. So look at this and this and this. TS can be written as T on plus T off. So let us divide by Ts. We have 1 equal to T on by Ts plus T off by Ts. So now this T on by Ts, we will define it as D, which is the duty ratio or duty cycle. It's called the duty ratio or the duty cycle. And this T off by Ts, we will call it as 1 minus D, just 1 minus D, because the sum should be equal to D. There are only two states. P can be connected either here or here, no in between states. So T on by S is D. So therefore Ts can be written as DTS plus 1 minus DTS. So we have now converted this time into an equation based on D, that is a duty ratio. So duty ratio is a value that varies from 0 to 1. So this portion here will be DTS. This is DTS, and this portion will be 1 minus DTS. So what we have now achieved is that when we can say for a period DTS time, pole is connected to T1. For a period 1 minus DTS time, pole is connected to T2. So this is the way we will be describing the switch on off without confusion. And D is an important variable called the duty cycle or the duty ratio. Please carefully understand this particular variable. Let us now mark the period for which PT1 will be on as DTS, and the period for which PT2 will be on will be 1 minus DTS, or this is the period for which T1 will be off. So now with this definition of the operation of the single pole double throw switch, let us look at some waveform. So let me now divide the time in this fashion. This is DTS period, this is 1 minus DTS period, this is the next cycle DTS period, and this is 1 minus DTS period. So on it keeps going. So this is one period. DTS plus 1 minus DTS is one period TS. So during this time, let us see what is the pole voltage with respect to the ground. So let us plot Vp. So during the time dts, P is connected to T1. So it has to be Vi. So Vi comes in there. Now during the time 1 minus dts, P is connected to T2 and T2 is connected to ground 0. So that is that point. Then dts period, again Vi and 0. So this is the voltage that you will see, the chopped voltage that you will see at the pole of the switch. Now what is the average value of this particular wave shape? We will call that one as Vp average, and from this relationship waveform we can find Vp average is, this is Vi in a cycle, Vi into dts, and here it is 0, therefore 0 into 1 minus dts divided by the entire time period ts. So you have Vi into d. This is the average value. Now what is the function of this LC? LC is a filter. It is nothing but an averaging network. So this is an averaging network or averaging circuit, and therefore V0 is the average of Vp, and therefore V0 is equal to Vp average, which is equal to Vi into d. So the relationship between V0 and Vi is Vi into duty cycle duty ratio. And note that d is a value between 0 and 1, and therefore V0 is always less than Vi for the circuit topology. Therefore it is called a step down or a buck converter. So this is the first primitive DC-DC converter circuit that we have seen.